In this video, I'm going to tell you what the Church-Turing thesis is. I'm also going to talk about the different classes of languages that Turing machines define, and I'm also going to talk about the different classes of problems that Turing machines can help us define. At one point in time, our notion of what computable means was a bit fuzzy, and there was some discussion about what this word meant. What was an algorithm? Alan Turing put forth his idea of Turing machines, and we've already talked a bit about what Turing machines are and seen some examples and how they work. But other people put forward different ideas, and you may be familiar with lambda calculus. Lambda calculus, on the face of it, is something that looks very, very different from Turing machines. And it can clearly be used to do computations. And so the question was, what does the word computable mean? What is it to be computable? And there were also different variations on Turing machines with different levels of power and so on, it appeared. For example, we can ask, does the Turing machine have one tape or many tapes? In our definition, we saw that we had one tape. It was infinite on one end, but had a left end. But what about if you had it infinite on both ends? Does that give you more power? We also considered Turing machines where the alphabet was simply a 0 or a 1, but maybe putting more symbols in the alphabet will give you greater power, or maybe not. Also, in our definition of Turing machine, the tape head was not allowed to stay in the same place. On each step of the computation, it moved either left or right. And then we also have the question of non-determinism. Turing machines, as we've defined them, are deterministic. But does non-determinism give you more power? Well, the interesting conclusion is that all these variations on the Turing machine are equivalent in their computing capability. And we show this by showing how to emulate or simulate, if you will, one sort of Turing machine on another sort of Turing machine. So, for example, what about a Turing machine with multiple tapes? Is it more powerful than a Turing machine with only one tape? It might be possible, you might think, that we could perform some computations on that sort of a Turing machine that we could not perform on a Turing machine with only one tape. But we can show that, no, that's wrong. The additional tapes do not buy you any additional power. And we can do that by showing how to simulate a multi-tape machine using a machine that has only one tape. So it turns out all variations on the Turing machine have equivalent computing capability. If a function is computable, it doesn't really matter whether you define that using a Turing machine of one form or another. The definition stays the same. And then it turns out that Turing machines in lambda calculus also have equivalent power. So the conclusion is that there really is only one notion of computable. Okay? And so that is the Church-Turing thesis. The thesis is that when we say something that is computable, it means it's computable by a Turing machine. So an algorithm is something that can be executed on a Turing machine, no more and no less. We don't use lambda calculus as our benchmark for definition, but the lambda calculus is exactly as powerful as Turing machines. And lots of other forms of computation are also this powerful as well. Now, this might be a good point for me to mention one more thing about Turing machines. And that is that you may have heard of something called the Turing test. And I just want to say right now that anyone who uses Turing machine and Turing test in the same sentence is probably very confused. I suppose my last sentence just used both those terms. But the Turing test is something altogether different than the Turing machine. The Turing test has to do with artificial intelligence and determining whether a computer or computer program displays human-like characteristics, whereas the Turing machine is used in a much more rigorous definition of what computability is. The Turing test is something that's widely seen in popular entertainment and the media and so on, and discussed sort of loosely. The actual paper was interesting to read. It's not a technical paper, and there's not a whole lot of technical material behind the Turing test. It's a very clever idea that's been widely misused and misrepresented in the media. It's really a overly strong test for whether a computer program has human-like intelligence, but it has nothing to do with Turing machines. So please don't get Turing machines and Turing tests confused. The main thing they have in common is that they were both thought of by the same guy whose name was Turing. Given a Turing machine, you can test whether a particular string is in a language or not. You put that string on the tape, and then you begin the Turing machine running on that tape. The Turing machine will either halt and accept, or it will halt and reject, or it may not halt at all. It may go on with an infinite computation. And that allows us to define several classes of language. So here again is my language diagram, and this is a Venn diagram, to be sure. Each of these bubbles represents a class of languages. I like to say a class rather than a set of languages because, after all, a language is a set itself. A language is a set of strings. So in this bubble, marked decidable, we have the set of all languages. Or, to say it another way, we have the set of sets of strings. I prefer to say the class of languages, with class being a synonym for set. So regular languages are the simplest sorts of languages. Then we have context-free languages. And then we have the three remaining categories. The square here represents the set of all languages. If a language can be decided by a Turing machine, then it's a decidable language. In other words, if an input can be determined to be in the language or not in the language by some Turing machine that always halts, then the language is decidable. Okay, and we say that that Turing machine decides the language. A decidable Turing machine or a decider will always halt, either accepting or rejecting as appropriate for the input string. On the other hand, we have some languages that are not decidable. Okay? Some languages are Turing recognizable, but not decidable. Sometimes we call these languages recursively enumerable. Such a language can be recognized by a Turing machine. In other words, if you start the Turing machine with a particular string on the tape as the input, and you begin the machine running, the machine will definitely accept if the input is part of the language. But if the input is not part of the language, the Turing machine may not halt. If it does halt, we're guaranteed it will say reject. In other words, we're assuming the Turing machine is truly correct and not full of bugs. But for languages in this category, there is no Turing machine that will decide them. There is no Turing machine that will always halt for every conceivable input. There are Turing machines that exist that will halt for every valid input, that is, for every input that is a part of the language. But there is no Turing machine that can be guaranteed to halt for all inputs and have the correct answer. And then you have the languages that are outside of this bubble, those languages that are not even Turing recognizable, or sometimes we say not recursively enumerable. And these languages are very complex beasts. There is no Turing machine that will halt on all inputs, even when those inputs are guaranteed to be elements of the set, elements of the language. So we can't even recognize elements that are in the language, as well as being unable to recognize elements that are not in the language. Now, I also note that there's an equivalence between languages and problems. Okay? Any yes-no problem can be turned into a language. The input is a description of the problem. And we can run our Turing machine on it, and if the answer to the problem is yes, the Turing machine should accept. And if the answer is no, it should reject. So the language consists of all those possible problems in that particular kind of problem area for which the answer is yes. Let me give an example. Imagine trying to determine whether a graph is fully connected, whether all the components are connected. If you are given a particular graph, it is either a connected graph or an unconnected graph. And that is something that is easy enough to find, and that's a decidable problem. Okay, so we can say that the input will be a specification of a graph, and the input is in the language if it's a specification of a graph that is connected. And if it is not a graph that is connected, if it specifies a graph that is unconnected, or if the input is somehow invalid and doesn't describe any graph at all, then it's not in the language. So we can take a kind of problem such as the graph connected problem, and we can encode all instances of that problem into input strings, and that defines a language. Okay, so there's a correspondence between languages and problems. So we can talk about decidable problems or decidable languages. We can talk about Turing recognizable problems or Turing recognizable languages.